Yes, we can see. We can see your slide. This is fine. Yes. Yeah.
Okay, good. Okay, therefore, unfortunately, I started later, but I will speak about new direction in elastic turbulence and viscoelastic channel flow. Elastic turbulence, it means that Reynolds is small, much below 1 or below 1, and Weizmann is large. Therefore, it's different regime. But I will start with Newtonian fluid because I will speak later on about viscoelastic flow in parallel shear flow. Now, in Newtonian fluid, Newtonian pipe flow, it's known already for at least 140 years that Reynolds, in his classical experiment, observed the transition to turbulence at Reynolds order of 2,200. But later on, Rayleigh, and after that many others, shows that this flow is linear stable. And that was big confusion for many years, and only for last 40, 30 years, the problem more or less resolved in Newtonian pipe flow. In polymer solutions, this question was becomes important only several years ago. And before that, I will speak about this polymer viscoelastic parallel shear flow. I will speak shortly about what property of polymers which is important for flow. Therefore, polymer in equilibrium, long linear polymers in equilibrium exist in so-called equilibrium coil. It's random coil, which if it's will be inserted in shear flow, it will be stretched. And stretched and elongated, but in shear flow, it cannot be elongated till the end. And only in strong flow, like elongation flow or chaotic flow, it can be stretched completely. Now, this model can be simplified if we consider the linear elasticity, and then linear elasticity, using linear elasticity for polymer, we can speak about Aldred B model. And in this model, if it's linearly elastic, it will be stretched indefinitely because stress is proportional to the length, and that's it. Now, if it's finite, in this case, we can use very widely used so-called Finney model of a finite extension nonlinear elasticity model. Then you can see that by applying force, this elasticity, this force going earlier, going almost linearly up to about 30%, and then started to grow up to infinity when the full length of polymers will be approached. Therefore, that's the main physics of behavior of polymers in the flow. Therefore, it will be stretched, and being stretched, it introduces new additional field, elastic stress field. This elastic stress field appears therefore as a result of stretching of polymers. If you consider simple model like dumbbell model with two masses connected with linear spring, we can see that actually this elasticity of this elastic stress field will be proportional to the conformation tensor. R is end-to-end distance of the stretched polymer, and G rigidity modulus. Therefore, if we know this R, we can construct and calculate in this model in Aldred B, we can calculate this polymer elastic stresses, besides these stresses that appears due to dissipation of viscosity. Then, instead of one equation that was discussed mostly in this conference, in principle, we have two equations. Now, in these equations, we have Reynolds very small. This nonlinear part inertial part is not important. And we have equation, linear equation, with additional term, which coming as back reaction from this equation, and this equation for elastic stresses. You can see that this equation actually different from Navier-Stokes equation, because this equation is elliptic and this parabolic. There is no Laplacian V, and behavior can be different. Therefore, we cannot expect that nonlinear parts that appear only in this equation, and this is nonlinear part, will give about the same behavior of the flow as single non-Newtonian single equation for velocity field. Therefore, in this case, we have two control parameters. One is Reynolds, everybody knows, and Weizmann, which is instead of velocity here, it's velocity gradient multiplied on the longest polymer relaxation time. Now, additional parameter beta, which ratio of elasticity of solvent and elasticity of solution, is usually fixed in experiment, because you take specific fluids with specific solvent, and it means that it's fixed viscosity and specific concentration polymer and specific polymer, and then concentration viscosity of solution also with specific, and this number. Changing beta, it means the change solvent or change concentration of polymers or change polymers, and that's usually not so trivial an experiment. Therefore, first I would tell several words about this, mostly investigated in details, the elastic instability and later elastic turbulence and flow with curvilinear streamlines. In this case, we have very well-known mechanism which build on hoop stress. Hoop stress, it's first normal stress difference mostly, because first normal stress difference is difference between component of elastic stress tensor in the direction of flow and perpendicular to direction of flow. Usually the component perpendicular in direction of flow is very small. Therefore, everything will be defined by this part parallel to streamwise velocity. And in this case, when polymers mostly will be stretched along this streamlines, and then any deviation from these streamlines in direction perpendicular to streamlines can produce the force, which is bulk force, directed to the center of curvature. If curvature is going to zero, this mechanism is inefficient. And that's why first I will show you a couple of examples. One is Coet-Taylor flow between two cylinders, classical example of this flow with curvilinear streamlines. And that I show you experiment with patterns that appear above the threshold, and then in a much higher Weizmann number, higher value of velocity gradient, we observe the power spectrum for velocity, and that has specific decay with exponent order of 3.3, which is much larger than decay exponent in the case of inertial turbulence. Therefore, it means that this flow, which described by such kind of decay exponent, is spatially smooth and random in time. And that's called elastic turbulence. And elastic turbulence, we first investigated the details in this experiment. It's a swirling flow between two disks, and we can measure precisely torque momentum. We can make measurements of velocity field by, at that time, we measure with LDV measurements, local velocity field, but with good resolution and time. And we visualize flow from below. You can pay attention that we taken only 80 ppm of polyacrylamide, which is very long molecules with huge molecular weight. And if you stretch completely, it's about 70 micron in length. And C star, it means that characteristic concentration at which polymer solution is already not dilute. It's about 250 ppm, therefore it's in dilute polymer solution. We have a solvent made of water with saccharose, with high concentration of saccharose. And since we work at very low temperature, 12 degrees, the viscosity of solvent was 320 times more than water, and of solution it's about 420. Therefore, that's a typical example of elastic instability and elastic turbulence in flow with curvilinear streamlines. And this elastic turbulence would be observed above the elastic instability at characteristic Weizmann number, about 3-4 times larger than critical to solution. We observe the following flows: that sharp decrease in flow resistance. That's characterized here. It's two different gaps, 10 millimeter and 20 millimeter. And that's the normalized friction factor. And we can see that first we have transition. In this case, a transition hysteretic, and then transition, and this continuous transition to flow with large fluctuations. And in this case, this large fluctuation appears about 3 times larger than transition value. Another very important, and actually this critical characterization of this elastic turbulence is velocity power spectrum. And you can see that in this case, we have a rather large range, about 1.5 order of magnitude, decay with decay exponent about 3.5. And third is efficient mixing. And this you can see it's Reynolds below 1, much below 1, but you can see that flow is random. And that's we visualize with plastic flakes. Therefore, that's characteristic 3, very important characteristic that defines the elastic turbulence. Therefore, in spite of the fact they call turbulence, it's chaotic flow with this specific property of this power spectrum, continuous power spectrum. Now I will switch to the another configuration. It's channel flow with 2 obstacles, and we concentrated on this region between 2 obstacles. What is different now? The difference now that it's parallel shear flow channel, it's clear. But in between, first you have linear transition. And linear transition, it happens because you have some specific property of this flow, which I will describe shortly. And that's visualization of this flow with strict visualization called, and it's close to transition. And you can see it's actually a curvilinear trajectory exists, but mostly it's very difficult to see 2 small vortices attached to the wall of obstacle. The characteristic sizes here, it's 700 micron between them, and 300 micron is diameter of this obstacle. Therefore, all region it's just 700 on 300 micron, and everything happens here. Now it's much larger Weizmann. You can see two vortices here, counterpropagating vortices with parallel shear flow. Therefore, it started as flow with curvilinear streamlines, and then continue and got 2 vortices with parallel shear flow. And then we want to see what happens later. Therefore, first of all, I show you measurements of friction factor. And this friction factor was measured by measuring pressure difference between 2 points. Between 2 points here, sorry, turn back. is pressure difference here we measure between this and this point, in this point, and we measure with balance, we measure the flow rate, and that gives you information about three different Weizmann numbers. This is biggest, three different elasticity. Elasticity is ratio of Reynolds, of Weissenberg to Reynolds. Reynolds is small, Weissenberg large, and you can see that we have this largest elasticity number, and then we have this strange behavior. We didn't expect this. Actually, drag reduction and re-laminarization. Then smaller elasticity, we have still drag reduction regime, and small elasticity order of 11, we don't have this part. Now you can see that this slope is 0.5 as expected for normal mode instability, linear instability. Here it's 0.2, and then it's minus 0.2. But it's not important now. What is important, we can characterize this transition for this highest elasticity, and you can see this characterization by measuring several parameters. It's velocity, RMS velocity fluctuation of streamwise velocity, average streamwise velocity, and this is average streamwise velocity. This is average vorticity and ratio of pressure fluctuation at 2 points. And you can see all of them have exponent of increase 0.5. For transition, it's definitely to single mode. Single mode has oscillations. These oscillations frequency going linearly with distance from transition. And that's Hopf bifurcation, which usual, in linear instability is one of the known transition. But besides that, we see that vortex, which appears here, two vortices, they started to grow and grow linearly also with Weizmann. And that's another mode which growing up to the point this two vortices completely fill this space. And that's reported here. You can see this velocity and vorticity field for different Weissenberg, and that's close to the maximum. You can see two vortices, counter-propagating vortices with parallel shear, with parallel streamlines. Therefore, in this case already, the mechanism of instability based on Hopf stresses doesn't work. Now, first transition is here once more. It's linear transition with Hopf bifurcation. Then we have transition regime with big fluctuation in friction factor and also at velocity. And then another transition towards the elastic turbulence, which accompanied by elastic waves. And it's first system we observed elastic waves. Before, in all systems with curvilinear streamlines, we didn't observe elastic waves. Now, besides, we measure also spectra. Here, spectra of pressure spectra. It's pressure spectra with index about 3.2 plus minus 0.2. And this, it's span-wise spectra, span-wise velocity spectra with index 3.4 decay and some peaks, oscillations peak, and or velocity peak. Now, I can show one of these video because I'm not sure that I will have time for both. You see, this is motion, two vortices with many, this fluctuation of singular fluctuation. It's vortices. It's a wall perpendicular to this plane. The vortice is perpendicular to this plane. Now it's the same, but for higher Weissenberg is on the end of this line. You can see the same vortices, but much more fluctuations. Therefore, that's actually what we observe in this case. But
Victor, we have 5 minutes left.
That's it.
Yes.
Okay. I don't know what I can explain. Okay, at least I will speak about this. It's very important observation. We observe this elastic waves. The frequency of elastic waves, we measure this part is above instability, linear instability, and this Hope oscillation, linear dependence on Weizmann, then transition region, and here new instability with nonlinear dependence on Weizmann for this frequency. Then we measure velocity field by cross correlation between 2 points on line which going in streamwise direction, and then we change the distance between 2 ends, and cross correlation show you by deviation of peak from 0 is measure characteristic time for propagation of these waves, and that's slope, it's velocity of these waves for given given Weizmann. And here the dependence of speed of elastic waves as function of Weizmann, and that's a law. I should tell that we measure this already for several flow configuration, and all flows besides has this universal exponent, and this coefficient also the same, but only for streamwise propagating waves. For span-wise, it's different. Okay, I didn't speak about this theory, but it doesn't matter. It's actually, that's what important, these waves. Now, then we try to understand what is reason for re-laminarization. And reason for re-laminarization is actually interactant of elastic waves with vorticity. Now, what we show is that, first of all, friction factor behaves, that's intensity of elastic waves behaves for different elasticity in this way. For largest elasticity, it's here, it's going up in the elastic turbulence regime, and it's suddenly going down. Now it's in a log-log presentation. It's a rather good exponent in this case. But then we look on this friction factor also going up and then down, and this point going transition from up tendency to decay. And then we put friction factor as function of intensity of elastic waves, and we see that it's actually correlated with each other. The most important part, of course, it shows that these vortices that you can see also here in elastic turbulence regime, that these vortices, intensity of these vortices also will correlate with intensity of elastic waves. But this experiment we didn't finish yet. It requires very high spatial resolution and very high frame per second of the camera, which we reached only recently. And that's only to show you this large, this vorticity, fluctuating vorticity for different, its biggest elasticity, 28,000. And that's a transition regime. And here it's beginning of elastic turbulence regime. It's much more. Therefore, that's the mechanism, but I don't have time to describe what is the proposed new mechanism for amplification of these vortices or fluctuations. Now, the next experiment we made in channel, which full length about half meter, is big. The thickness 0.5 millimeter and width 3.5 millimeters. We excite this, we have special prearranged perturbation. We put here array of obstacles, 3 rows of array, and each array 11 obstacles, and that's perturbs the flow on full length. And then we look what happens in this case. As we measure the friction factor, you can see this transition, and this transition is already non-linear, and I will explain why. First of all, it's not 0.5, as you can see. This is elastic turbulence regime and then a drag reduction. But we measure also RMS of pressure fluctuation, RMS of streamwise fluctuation, and you can see this transition continues as here, but exponents very different from 0.5. But most important factor is appearance above the instability, not single mode, the most fastest growing mode, like in linear instability, but continuous spectra. And that's just above instability. Therefore, it's definitely not linear instability, but non-model instability, as we see. Therefore, that's different. It's streamwise velocity spectra at different Weizmann. Here it's transition regime. That's continuous transition, also continuous transition reached by high Weizmann, and then elastic turbulence 3.2, and then reduction to this, it's drag reduction regime. Therefore, in this case, if you look not on streamwise, but on span-wise velocity, we observe also peaks. These peaks we show only in linear log scale, otherwise it's difficult to see, and we exclude this part related to decay. And you can see that intensity of the peaks going sharply with Weizmann. Therefore, the elastic waves, these elastic waves, and these elastic waves also are characterized and have exponent close to what we observed in previous flow. And that's what important observation in this flow. We observe coherent state. And this coherent state presented here during a cycle, it's cycle specific. And we observe, first of all, this is streaks. The first streaks that going in this direction, and this streak going in this direction. We subtracted, of course, average flow, mean flow profile, and that's why we have this counter-propagating streaks. Now, this...
if you want to have time for one or two questions, I recommend to stop here.
Yeah, but I didn't speak. Maybe I will take another couple of minutes at least for a reasonable question, because that's important, the most important.
Okay,
part.
take another minute, then we can have one more question.
Therefore, that's a coherent state. Now, we define the cycle and show that this cycle is, frequency of cycle is equal to frequency of elastic waves. Therefore, it's controlled by elastic waves. Elastic waves pump energy into the cycle. What is important is we observe these cycles and coherent states and elastic waves. We observe in a limited range of length scale, only up to about 200. Therefore, we started here. 0 is end of cylinders for perturbation, obstacles, and then it's sharply going down from about 60% to about 4%, and then going up, probably due to intrinsic instability, which we have, and then more or less constant. And in this range, we measure all these measurements we made in this case. And in this case, we observe also decay of intensity of elastic waves. And you can see they also decay up to 200. Therefore, this correlation, once more, shows that actually these elastic waves are source for pumping energy into the flow, and the smaller intensity, the smaller this friction factor, the smaller fluctuation, and so on. And when the fluctuation intensity of elastic waves becomes very small, then this whole structure disappear. But we have till the end fluctuation of velocity on the order of 2–3%. Now, I wanted to show you.
If you want to have one question, we need to stop here.
The last point, what I want to say is that is the same, almost the same channel we used without any perturbation, and we observe similar phenomena. That's we call this universal property. We observe more or less the same phenomena, and without any perturbation, is the same thing, the same channel. Okay, I should stop here because we don't have more time. Yes, okay. I finished.
Perhaps one question from anyone here?
Yes.
Any questions? Yes, while Mike gets set up.
Set up. Okay. This setup or previous?
So Victor, I think we have to move on, but there's going to be a discussion session at 4 o'clock. So
And-
if you at 4 o'clock a time, there's going to be a discussion session. So
Tomorrow?
No, today.
Today at 4 o'clock, at
Okay,
6
yes,
o'clock
maybe,
at my time.
yes, around 4
Okay.
o'clock. So join us
Okay.
then. Thank you very much, Victor.
Okay, good. Okay, thanks.
So